Thank you. Thanks all of you for coming back for number 2 at 9 o'clock in the morning. So I hope you remember everything I said last time and everything Antoine had said in the morning before me yesterday, because it will be related. So my goal today is to present another conjecture. This one is even a stronger statement, which might surprise you that I would do that since we know almost nothing about the previous one. I saw there were very few cases that we could treat in the previous one, but now I'm going to make a statement, a claim that is even stronger, even bolder. But from my point of view, it gets even more interesting when thinking about the geometry of periodic points and preperiodic points in families of maps, because it relates to a lot of the things that I've been thinking about for many years, especially the theory of stability in dynamical systems, bifurcations. So you'll see that it'll tie in with some other themes as I go. So my goal is to present the conjecture first, to make the statement, define the terms. It will look technical. I apologize for that, but I want to make the statement precisely, and some of you have seen it before, but I know many of you haven't. It's based on this is joint work with Myrto. And then I want to describe various consequences, in particular other conjectures that are special cases of it, some of which are maybe surprising because they're formulated differently. Okay, so here's I need a little bit of notation, a little bit of setting. Remember, so last time I was thinking about one endomorphism, say, defined over the field of complex numbers, where the degree of f I called d, which I assume to be bigger than 1. It's not an automorphism. In Antoine's talk, he mentioned briefly an invariant 1-1 current that one defines associated to this one dynamical system. So let me just say I'll use the notation T sub f to correspond to a limit in the sense of distributions of pullbacks by iterates of, for example, the Fubini-Studi form. So here omega naught, let's take it to be the Fubini-Studi form, or any smooth 1-1 form that gives us a volume. We can normalize it so that the volume is equal to 1 of the projective space. You do this sequence of pullbacks of these forms, and they converge weakly to a positive 1-1 current that I will denote by TF. An important feature of this current is that it's, of course, invariant under this pullback operation. And then, I guess this notation also appeared in Antoine's morning talk, which is if you take this TF and you wedge it with itself n times, it gives you a probability measure, which I'll denote by mu f. So n, remember, capital N is my dimension. So this measure, so it's a probability measure, which he did not speak to the dynamical significance of this measure, but many of you are well aware that this measure is the unique measure of unique probability measure of maximal entropy for this dynamical system. It also reflects the distribution of the repelling periodic points. Its support is what we call the Julia set, or the small Julia set. I'll call it the Julia set. So these are all theorems. Of course, all of this there are lots of theorems involved in what I'm saying and what I'm writing. So let me just write down a few of those things. So this is the unique measure of maximal entropy, up to scale. It also is the distribution, the limiting distribution of the repelling periodic points. These facts were proved by Briand and Duval in, I guess, a pair of papers. When are they? 1999, maybe? 2000? Around then. Okay. So this measure plays a very important role from a dynamical point of view. If this map happens to be defined over a number field, say it has rational coefficients, so if f is defined over some k, which is a number field, there's some arithmetic structure underlying the dynamics. And Antoine also introduced the canonical height. So let me just use some notation. I won't give formal definitions, and I won't even use it for the statement of the conjecture, but I want you to have this in the background. So if it happens to be defined over a number field, if you start with sort of your favorite choice of height, for example, take what's called a standard or a naive Weil height on the projective space, then the canonical height, which I'll denote in this way, I guess this came up also in Serge's talk, can be defined as follows. One looks at the growth rate of, you fix your favorite height, one looks at the growth rate along orbits of the regular height. It's known that it, sort of through the Weil height machine, the theory tells you that it will grow like the degree of the map. And then it turns out this limit actually exists. This was really first introduced in this form in an article of Call and Silverman, and I think that was 1994. But as Antoine mentioned, this really goes back to an idea of Tate from the 1960s in his construction of what's called the Néron-Tate canonical height in the context of abelian varieties. So it's really an idea that goes back to Tate from the 1960s, I guess. Okay. But I mentioned this particular height in the context of what I'd just written down because this also was mentioned in Antoine's talk. So heights, in some natural way, have a decomposition. I'm going to put an equal sign here because I'm not going to define these objects, and what I'm writing is a little bit sloppy. But the point is that these heights have what are called local decompositions. So you can express them as some infinite sum over all what are called the places, the absolute values on your field up to some normalization. So there are these functions defined what we call locally. So there is this decomposition of the height function, and the relation to what I had already written in the complex dynamics, if you take an Archimedean place of this field with sort of a standard embedding of k into c, and you run the complex machinery, this TF can be seen in this data. The TF is just, this is something that Anton wrote in his talk, just you have a standard, you choose an Archimedean place with the standard embedding of your field, and this local height locally, say choose an affine chart, anyways, is a potential for this particular 1-1 current. So to give you just a hint of a relation between these arithmetic tools that are often used and the complex dynamics tools that we, and here, most of us use more often. Okay. All right, so that was just a little hint of some of the arithmetic that goes behind this. So now let me introduce families and make the statement of the conjecture, which will not involve the height, but the proofs do. Oh, I forgot I was supposed to use the buttons. Okay, I guess I'll do that after. All right, board number 2. Is that right? Wait, where's the third? Oh, the third one's just behind. Okay, all right. All right, so the setting now is that I'm interested in a family of maps. Oh, let me have a parameter space. So let's say capital lambda is, well, in general, it could just be some complex manifold. And maybe we're interested in a holomorphic family of maps on the projective space. Okay, so by family, I really mean a family of maps, so it's acting as the identities, just fixing a parameter, and then this is, say, f lambda of z, so each of these is a morphism of the projective space of the same degree, of this degree d. Of course, I want phi to be holomorphic, so they all fit together as a holomorphic family. Now, if I assume that lambda has more structure, if I assume, for example, that it is an algebraic variety, say a quasi-projective algebraic variety, and if phi is a morphism, then I say it's an algebraic family. So this is an algebraic family. If, let's say, lambda is a quasi-projective complex algebraic variety, and then phi, I have to assume, respects this algebraic structure on the variety lambda cross Pn. So phi needs to be a morphism. Okay, so now the statement. Okay, so what is the statement about before I make the statement? So if you remember, yesterday, there was a conjecture about the geometry of the preperiodic points for one map and how they organize themselves inside Pn. Which subvarieties of Pn can have lots of preperiodic points? And so now I'm asking exactly the same question. Which subvarieties of this product can have lots of preperiodic points? And the goal of the conjecture is to characterize exactly which these are. Which subvarieties have lots of preperiodic points? And by subvarieties, I really want ones that are families of subvarieties. So in my picture, I have my parameter space down here. Say I have some projection. I have my product, of course, over any lambda. I have a copy of Pn, and I have my dynamical system. And a family of subvarieties. Of course, I really want it to be over all of lambda to make sense in this context. So you should picture some kind of family of subvarieties that I'm going to call curly x. Okay, so here's the setting. All right, so phi as here, be an algebraic family of maps on Pn of degree d, which is at least 1. Let curly x in this product be a family of subvarieties, or flat, irreducible, flat over lambda, I should emphasize. Flat over lambda, irreducible, complex, algebraic subvariety of, well, period. Algebraic subvariety. I'll come back to the word flat in a moment. And the statement then is that the following are equivalent. It's just two, but I'm going to write it. I want to give them names or numbers. So the first condition is that X should have a Zariski-dense set of preperiodic points. For phi. I'm working over the field of complex numbers, remember. So, you have your periodic points of phi exist in families, but I'm just looking at individual points over the complex numbers. So X has a Zariski-dense set of preperiodic points for phi, should be equivalent to the following condition. So here is a characterization, which is decidedly unsatisfying when you see it for the first time. In fact, maybe you see it for the 15th time or more. It's not, anyways, you'll see it. Okay, the statement is the following, that it will be a Zariski-dense set of preperiodic points if and only if, oh, I forgot to define the current in families. Okay, well, I'm going to write something down and then define it. If a particular power of the invariant current for the family does not vanish on X. where, and then I have to define this thing for you, but where R is what we call the relative special dimension. It'll disappear for a moment, but it will reappear at the top. I need to spend some time defining the terms and clarifying what it all means. Can you see it? Can you see the full thing? Okay. Oh, okay. With the glare of the lights, I actually can't see it at all. But okay. So, all right. So, just first of all, again, what is the setting? My X, remember, should think of as a family of subvarieties parametrized by lambda. The word flat, you can essentially ignore. The point that I want is that it's constant dimension. It's a family of algebraic curves, or a family of points, a section even over lambda, or a family of hypersurfaces. Whatever it is, it's a family, and just think constant dimension. Okay? That's really probably all we need, without any formalism from commutative algebra. Okay, so T phi is just like this TF, except defined for the whole family. So let's just make sure we have a definition on the board. So in my picture, which I guess I should, my schematic here, which I should redraw. So here I had my lambda cross Pn. I have a projection down to the parameter space. Here's my copy of Pn in the fiber. It's dynamics. If I project horizontally, shall we say, to the dynamical space, one can take your, say, our favorite form, our Fubini-Studi form here, pull it back, in other words, smear it out over lambda, and then do the same dynamical construction, and that's what this T phi is. So by definition, this notation with the hat, I've pulled from a paper of Charles and Roman. I think they use hat when they were referring to families, and so that's what this notation is. T hat phi is by definition, let's say I call that P naught, so I first pull back to get some nice 1-1 form across the whole family, and then you start doing the dynamics. Oh, I'm not going to have space, and then you normalize, and then you take a limit. So it's the same construction, it's just that we're doing it in a family. Okay? But one important thing to observe with this particular positive 1-1 current on the total space, just as with the other I didn't mention, it has continuous potentials locally defined. If you restrict to one of the fibers, you get back the TF. So this one in families can be thought of as via slicing or restricting the potential as just the TF on each slice. So it's really taking those TFs and gluing them together. But in a particular way that this family one, I should mention, it vanishes, for example, along periodic points. So if this happens to be, or preperiodic points, if this happens to be a parametrized family of periodic points, it's not necessarily a section, maybe it loops around in some way, this will vanish identically along the periodic points. Okay. So that's the first statement to make. I need to spend a little time talking about this particular power R, this relative special dimension, because I should say all of the content of the conjecture is in the definition of R. Okay. Yeah?
You said, so if you have a preperiodic point, the T will vanish?
It will vanish along that subvariety, yes.
Isn't that a contradiction with the conjecture?
No, it is not, as we will see, because it's all hidden in the definition of R. It's all about the definition of R, as you will see. Right, so if, yeah, I mean, that sounds already funny. Like if X is the thing, then that R is exactly the dimension of X, and then it will actually not vanish. Dimension of the fibers of X, I should say. So yeah, I will come to the definition of R in a moment. And we'll see how it vanishes. So it vanishes along here. So T along this point. Well, not point, I shouldn't call it a point. Preperiodic subvariety, I should say, if it's just a single point in a fiber. Okay. Before I give the definition, however, it's very important, and I should have mentioned this right from the very beginning. So this conjecture, so I wrote this in the paper with Myrto, but it's not that we sort of came up with this out of nowhere. It was very much inspired by what happens for families of abelian varieties. Although they formulate it in different language, but this is very much inspired, and so I'm just going to say this once, and then I won't say anything else about families of abelian varieties, I don't think. There's a theorem of Gao and Habegger. So this is in a 2023 preprint where they prove what they call, there's a lot of this language, so what they call a relative Manin-Mumford theorem, or it includes what's called a uniform Manin-Mumford theorem. They also prove a uniform Manin-Mumford theorem. So there are various names for statements like this. The main point is what they call a Manin-Mumford in families version, which implies the theorems, the conjecture and the theorems that I mentioned last time. Although even that is not totally obvious until you see the full definitions. But it's very important that I mention this. And I should say, for those of you who might actually be familiar with their work in families of abelian varieties, so condition 1 looks identical to their condition when you're dealing with families of abelian varieties. Condition 2 is equivalent, so in their case, condition 2 is equivalent to what's called maximal Betty rank. So if you're familiar with this work, I just want to mention this. That's what this condition 2 corresponds to in that situation, when it's a family of abelian varieties and X is a flat family of subvarieties of abelian varieties. Is the condition that X has what's called maximal Betty rank. So we think of this condition in parallel as something like X has maximal dynamical rank or phi rank. But I won't get into that. I just want to mention it. So credit is due to them for the idea. This implies, by the way, I mean, I put this in quotes. This implies, in particular, again, if you're familiar with a lot of this theory, for example, the theorem of Lars-Kuhne, which says that, sort of in the original setting of Manin-Mumford, curves and their Jacobians, that they're uniform bounds on the number of torsion points on a curve and its Jacobian over the whole, depending only on the genus. So for e.g. Kuhne's theorem. So, okay, this is just remarks for those of you who know the background already. So these family versions of characterizations turn out to imply uniform bounds, although it's definitely not obvious from what I've written. Okay, so what is R? So I need to spend a little time defining this, and although maybe I should pause if there are other questions before I give the definition of R. Yeah. Right, so I haven't mentioned a bifurcation current at all. Right now it's just the family of currents for the dynamics, but indeed, for those who know what it is, and I will say more about that actually, I will tie this in because it turns out there are connections to stability, and indeed, it is not, and indeed, the family being persistently preperiodic would guarantee a stability statement. Absolutely. But that also requires then a bunch of definitions and citations that hopefully I will come to shortly, including of a number of people in this room. So hopefully I'll get to that. Yeah.
So the maximal Betty rank can alternatively be expressed as choosing generators for your lattice spaces that are moving them independently, right? Is there a characterization of this condition in terms of moving critical?
Well, we don't have periods. We don't have. Not directly, no, not directly. So for me, one of the things that made this statement, once we started to explore, okay, we take a statement about abelian varieties, let's just naively translate it into a statement about dynamics. It just got so much more interesting once we realized what this would suggest and what theorems are actually special cases of this. So I'm hoping to come to it. But no, there is not a direct way except in the language of these currents. Because we don't have a smooth, I mean, in a smooth abelian variety, of course, you have all of the torsion points moving nicely in a family, no collisions, no bifurcations, so we just don't have that. We don't have the basis, we don't have the universal cover, we don't have any of the machinery that they actually use to prove those theorems. So yeah, as you know. So, okay, what is this R? So I said the content of the theorem is really contained in what this particular power should be. So in words, this is sort of a minimal or smallest relative dimension or fiber dimension of a family of, shall I say, phi special subvarieties. I'll give a formal definition in a second, but by which I mean either preperiodic, or maybe I don't need to give a formal definition because I did last time, either preperiodic for phi, or if you remember, I went through this whole thing last time, or preperiodic, possibly preperiodic for something that commutes something, some endomorphism that commutes with phi. Something. A polarized or polarizable endomorphism. Sorry, I'm writing small, and those of you in the back probably will not be able to read this. Okay, so let me just say in words, R represents the fiber dimension, the relative dimension of some family of subvarieties that containing X. So I have my X, and I look for the smallest family of subvarieties containing my X, which is invariant for phi. That's what this is. So what I actually wrote was the smallest relative or fiber dimension for a family of varieties, that are called phi special, containing X. And so I'm using phi special to indicate the characterization that I mentioned last time. For one map, it was you expect the variety to be either itself periodic or preperiodic, or perhaps for something that commutes with that map. So I want to look for the smallest thing containing my X, and that's the actual power that I would like to take. Yeah?
Don't you need to restrict X to some open subset over lambda? You could imagine that there is a family of special varieties that is over a Zariski-dense subset of lambda, and that's not X.
Right, and that's okay. I would allow that to be. So I mean really the relative dimension, so then it wouldn't be every single fiber. Oh, that it might not. Well, okay. My X should be Zariski closed, and so when I pass to the closure, it should be okay. So it might not be special in every single fiber, but it's special for the generic So the formal definition, I would write it over the function field. So I don't care if it fails. Thank you. Yeah, I don't care if it fails to be special for a particular family of fibers. Thank you. I haven't written a formal definition, but I would write it in fact to say over the function field the same concept of special that I wrote last time, and I'm just being lazy here. But thank you for mentioning that, because to be precise. Did you have a question? No. Okay. Yeah.
So for a family of periodic points, it's 0.
Correct. So if I have parameterized, so if X happens to parameterize a periodic point, say a fixed point, then yes. So then it itself has relative dimension 0. And this relative special dimension is also 0 because it is itself already special. And so in that particular case, every point is periodic, fixed, say, if it's a fixed thing. So certainly the periodic points are not only Zariski-dense, but dense. It's equal to every single point. So I'm taking the 0th power of the current. What is the 0th power of a current? It's just the constant function 1. So in other words, I'm looking just at the current of integration along x, which is a non-zero current.
So in the generic case, you expect the relative dimension to be
N, yes. Let's say that. Yeah, generically, this thing is n. Typically, you don't expect subvarieties, or we expect. It's not that I've actually proved. I mean, yeah. For typical family, for typical choice of x, you expect this to be n. You don't expect it to be trapped in the whole family inside a subvariety. So what would that mean? If you have n in the typical situation, what are we looking at? We're saying x sees the lots of preperiodic points if and only if it intersects the measures of maximal entropy. Then we're taking the maximal power of t. And we're saying, how does x intersect the Julia sets? The nth power is the family of measures. And it's detecting when x intersects the Julia set, which are, of course, containing repelling periodic points, which gets to my next point. But in a non-persistent way, unless it is itself, yeah, of course, special, but of course, I'm assuming it's a subvariety in the generic case. In a non-persistent way, which gets to my next observation. So let me bring number 1 down. I like how everyone was helping Rohini yesterday. Maybe I should employ that strategy. All right, so 1, and I bring 3 up. Thank you. All right. That's not a very good. Okay, if you are following along with my secret lecture notes, you'll see the formal definition of R written there. On page 7. Okay, there is a formal definition of what it means to be phi special. It's defined in terms of the function field. And then this relative special dimension is its fiber dimension. But yes, typically. So in general, R is something between the relative dimension of x. So it's a family of curves, that would be 1, and n. Okay. Erasers. Yes, shoot. No, sorry. Yeah, I wrote smallest dimension, and I was careful to write smallest dimension, not the smallest phi special. There is not a unique. So in the case of abelian varieties, if you're familiar, there really is a genuinely smallest invariant subgroup, or smallest what's called special, or flat family of subgroups that would contain your x. This is not the case for families of dynamical systems. There is not necessarily, and in their examples, a unique smallest special. You can have situations where your x is contained inside, say, the intersection of 2. Maybe x is a family of points, and it's contained inside the intersection of 2 families of curves that are special, but there isn't a small, and each of them are special, x is not, and so you get into trouble with intersections, you get in trouble with uniqueness. So there is a genuine distinction between, I wrote smallest, I'm really emphasizing the smallest dimension for a family of phi special. It's the minimal smallest, the minimum dimension. So things really get a lot more complicated because we have, dynamics in general are just, more complicated than the dynamics of an endomorphism on an abelian variety. That's what it comes down to. Should I leave this? Well, I can leave it for the moment. I won't need it just yet. Okay, what did I want to say? I wanted to mention, so Thomas made a quick comment about how does x intersect those periodic points, yeah.
And just because of P or subnet, so I'm a little confused. If you have two P special families, then the intersection should be P special.
So the intersection is not necessarily phi special, and an example is escaping me, although we include one in the paper, I think.
You can intersect preperiodic subvarieties and not get a preperiodic point.
That's what I want, and I'm just having a hard time coming. I mean, think of a two-dimensional dynamic, so a higher dimension, not one-dimensional. So think of like you're in P2, even just for one map, forget about families for a second. I want to take, say, a curve, two curves that are preperiodic that happen to intersect in a point. Oh, where their intersection point has an infinite, oh, okay, I like that. All right, so let's say you're in P2 and I take two curves, each of which map to some third curve that should intersect it, but in any case, but where their intersection point happens to have an infinite orbit is what you're picturing. Yeah, something like this. This can be done, and I'm just having a hard time coming up with an example. But they exist, and that's, yeah, and that's the kind of thing that can happen. Yeah, thank you. Yeah. Okay, so important to note that I wrote conjecture, but 2 implies 1 is known. I wrote conjecture. I want to emphasize the equivalence of the two conditions, but the challenge is really 1 implies 2. 2 implies 1 is known, which is not trivial. So let me say emphasize a little bit of what goes into that. So 2 implies 1. If you happen to know this particular power of the current is non-zero along x, then, well, so perhaps x is itself special, which would mean it has it has lots of periodic points even in families across, throughout the x. But as soon as x is, so the picture you should have in mind, and this is sort of the typical picture, sort of a generic picture to have in mind. So just one more time. So imagine again, so I have my x, which is some family, say, of curves. Okay, so imagine I'm projecting, and here's my family. So you know that for each fiber, for each particular lambda, there are lots and lots of preperiodic points. There's Zariski-dense in Pn itself. And as I mentioned earlier, for example, the repelling periodic points are dense even in the support of the measure mu f. And so in this generic case where that r, that special dimension, is n, meaning that, say, x is not trapped in some smaller family. So assume that the orbit of x maybe is going all over. But it may or may not intersect a periodic point or contain a periodic point in that particular fiber. But what you should picture is that the periodic points, so they are themselves parametrized by some algebraic subvarieties. But sorry for all the white, I should have used color. Anyways, the periodic points, each individual one varies in some nice algebraic way. But as many of us in this room know, of course, in families of maps, there's no reason to think that they're going to be organized in some nice way. They're not necessarily forming a good foliation. And so, unless you're in a family of abelian varieties, for example. But so what you have is they're moving, and your x should be moving through them. And so what you should expect is that x, what you would hope for, and what is actually true then, if you assume the positivity of that current, is that x is crossing, is passing through these periodic points. So let me mention some names. So so the ideas that go into this particular argument. So it's not, the definitions as I've given them are a little bit different than in some settings in the literature, but one can unpack the work that Raynaud did in the setting of bifurcation currents, he was specifically working for families of maps on P1, but he does some general work about currents and how the bifurcation currents detect intersections with repelling points. In the setting of working in families of maps on Pn and the theory of stability, I guess Christoph is here, right? Yeah, there you are. So Bartolo Bianchi and Dupont worked out the theory of bifurcation currents and conditions on stability for families of maps on Pn. And in their arguments, so the machinery, the techniques that they use to prove certain characterizations of stability, similar to what Raynaud was doing in the setting of dimension in maps dimension 1, give you the argument. And then Thomas' setting actually matches a little bit more what we did, so we could really copy a lot of what Thomas had written also in the context of studying sort of these bifurcation currents and families of maps. Anyways, let me not go into all the details. The details are in the paper itself, although I realized only as I was preparing the lectures, I don't know if any of you is the referee of this particular paper of mine with Myrto, but I'm more aware that there was like a key step that I forgot to mention, which was the trivial case of when X is special itself. So I apologize if you're the referee. I will fix that. Anyhow, so this 2 implies 1 follows from theorems and, well, proofs of theorems that are in the literature already. So 2 implies 1 is known. Okay. So if that current is positive, and if X itself is not special, then what you're seeing is these repelling periodic points crossing X. Okay, that's the upshot. The positivity of the current means the repelling periodic points are crossing X. And what we believe is that if you assume just any old periodic points or preperiodic points intersect X, then there have to be lots of repelling ones. So the content of the conjecture is saying, if X intersects lots of periodic or preperiodic points, then in fact necessarily it's intersecting lots of repelling periodic points. It's not like in dimension 1 where you have only finitely many non-repelling points. But even in dimension 1, this is not obvious, though I should emphasize that it's also known in dimension 1. So let me say a few words about what's known and then go into other conjectures, although I could pause and ask for questions again. How am I doing on time? 45. Okay. Let me look at my notes. What did I want to? Oh, I have an order of things. So if you actually are following along with my notes, it's a little absurd. I got it kind of carried away. There's a lot more in here than I will have time to discuss, because there's something like 10 typed pages just for this morning's lecture, which is I will not cover all of, but I want to say a little bit more about what's known. But just this comment, I'm hoping, gives you a hint that it will be tied in with the theory of stability, so I want to come back to that also. So let me just over here then say that, okay, so 2 implies 1 is known. The one-dimensional case is also known. The case of n equals 1, let's just take a look at what that's saying. So for n equals 1, so now I have lambda cross P1. So I have a family of maps on P1. What is a subvariety of lambda cross P1, which happens to be flat over lambda? Well, it's either the entire space, in which case the preperiodic points are obviously dense. We know, in fact, again, in every fiber, there are infinitely many periodic points for F. And so if your X happened to be the whole space, of course it is. Let's just check that the conjecture holds. If X is the whole space. So of course condition 1 definitely holds, and condition 2 would mean R is this relative special dimension. X is itself special, it's the total space. So the relative dimension is 1. The relative special dimension is 1. It's the fiber dimension. So it would say that is the total current raised to the 1 power, which is just the current itself, intersected with the current of integration on the total space, which is, you can ignore, and then it's really just saying that the current itself is non-zero. Okay, so it doesn't, there's nothing to show. I just want to observe that it holds in the trivial case where X is the total space. Where it gets interesting is the case where X is not the total space. So what does it mean to not be the total space? It would mean that you're either, say, a section over lambda, the fiber's only P1, so you can only then be a point, or a finite set of points. So maybe this is your X. It's following some point, so a section or a multi-section over our parameter space. And in this case, the statement reduces to a theorem that I had proved in a paper published in 2016, which was about, I guess going back to Mark's question, which was about the stability of a single point in algebraic families. And so the statement is, in fact, that conjecture becomes logically equivalent, in fact, to the theorem that I proved about stability of a single point. So I'll just say that it follows from this theorem when combined with, say, Montel's theorem of normal families. Let me say, if X happens to parameterize a critical point of your family, which is a case which is of great interest to many people in this room, people who focus on one-dimensional complex dynamics. So if X happens to follow a critical, so if, I should have a hypothesis. If X parameterizes a critical point for this family of maps over this parameter space. Again, this is a family of just maps on P1. If X happens to parameterize a critical point, then this condition is proved in a theorem of Dujardin and Favre that preceded. I was generalizing something they had done in the case of, say, when was that published? I don't know, 2008. And then when it parameterizes all the critical points, so remember I have this map phi, which is a family of maps on P1. When it happens to be all of the critical points, then this is contained in the work of McMullen from his thesis, where he showed that a stable algebraic family is persistently post-critically finite. That is the content of this theorem, of this conjecture in dimension 1. Okay, so this reduces to the statement that stable algebraic families for maps on P1 are either isotrivial, meaning they're all conformally conjugate to one another, or persistently post-critically finite, which in the case of dimension 1, I'm not going into detail because I didn't want to spend a lot of time on this, sorry. It doesn't go up anymore. But anyways, sorry for not going into detail. I just want to mention that the n equals 1 case is known and it's related to the theory of stability. So I want to say a couple words about stability in general now. But that is a special case. That statement, stable algebraic families are either isotrivial or persistently PCF, is a special case of this conjecture. And a known case. But so the surprise for us, before I go on, is just to say, as we were taking a statement, again, so it's going back to the beginning, we were taking a theorem that was just proved about families of abelian varieties, just seeing what it would say in the context of holomorphic dynamics on projective spaces, trying to figure out what the right language is and what the right power of the current should be, and then realizing that it actually connects to a bunch of, for example, this McMullen lemma or the theorems here, that, I don't know, it connects back to a lot of things that are of interest in complex dynamics that are not interesting in the context of families of abelian varieties, because they're stable. they're dynamically stable. Okay. So let me just say a word about this. I want to say what is the bifurcation current, since it's come up, and it's, of course, closely related to this. Actually, let me just write here. I can erase the heights. I won't say anything about heights. What time did I start again? What time? It was 9 o'clock, right? It was roughly 9. I have so much time. Sorry, guys. I'm going to go on and on and on. All right. Let me just... Okay. So I want to go through a series of sort of special cases to try to understand what does this conjecture really mean in various settings. Okay. So suppose for the moment now that we have an algebraic family of maps on Pn, and suppose that X is the critical locus of phi. Okay. Just redrawing a schematic picture. So the critical locus of phi, so for each individual map, remember the critical set is some hypersurface, some hypersurface inside Pn. If these are degree d, of course this is just where the Jacobian determinant vanishes. So this is some hypersurface of degree, I wrote it down in the notes, what is it, n plus 1 times d minus 1. So a family of hypersurfaces, so this is some family of hypersurfaces of degree n plus 1 times d minus 1. Here's my picture. All right, it's the same picture. I don't even know why I'm drawing it. I'm not sure it's helpful, but for me, it was always helpful to have a picture, even though I don't know that it clarifies anything. But there's my picture. Okay, so it's some family of hypersurfaces inside our family of Pn's. Okay, so in this particular case, so this is, again, a family of hypersurfaces. So the relative dimension of X itself is n minus 1. Okay, so the relative dimension of X, so this is my notation for the relative dimension, in other words, the fiber dimensions, because it's constant dimension, is n minus 1. So the relative special dimension this relative special dimension that I've introduced, so this R of phi x, well, it can only be one of two things. So that it's either n minus 1 or at n. Again, remember, it's a family of varieties that contain the x, which are either preperiodic or preperiodic for something that commutes with f, blah, blah, blah. Anyways, that's preperiodic, some invariant family of subvarieties containing x. So it could only be, say, x itself. So this case would mean x is itself preperiodic, so or preperiodic for something, or dot, 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 phi special. I'm just going to ignore this case. Every time you have to deal with that separately, I'm just going to ignore that. Let's assume for the moment, so this n minus 1 case would mean x is itself phi special. So let's just assume that means that it's itself preperiodic. So that would be, in other words, that would correspond to a family of what we call post-critically finite maps, that the critical locus is preperiodic. Okay, so in other words, i.e. phi is then a family of PCF maps. Okay, so that's what that would mean if the relative special dimension were n minus 1. Okay, the critical locus is itself preperiodic for the whole family. Now, unless n is equal to 1, we do not have a complete characterization of what families of PCF maps can exist. This is still an open question to give. In dimension 1, we know what they are. Either it's a trivial family, they're all just the same map, or it's a family of lattice maps coming from endomorphisms of elliptic curves. So in dimension 1 we know, but for general n, we don't know. One can build some families of lattice maps in higher dimensions, but I mean beyond that, I don't know that there are other examples known.
Does that commuting with featuring actually happen if it's the critical?
Can it? Well, if lambda is, for example, a full family, like let's say lambda projects dominantly the entire moduli space, then for sure no. But there could be particular family where for some reason, probably not though, and I haven't thought it through completely to determine in this critical locus case. I don't think so, but unless it's actually preperiodic itself. I think that would be, I don't think that can happen. I mean, or because you can build lattice examples in higher dimensions, like with an E cross E, maybe you could do something like that, but I don't know. Maybe there's some funny thing you could do, and I haven't really thought it through exactly what the exception should be, so I'm going to ignore that point. But again, for conceptual understanding, I just want to say, like, let's just say that this n-1 case is just, let's say, a persistently PCF family. And in that case, okay, just keep in mind, again, why does the conjecture hold? The conjecture should hold clearly. If you have a subvariety which is itself preperiodic, then necessarily, I mean, if the entire X is preperiodic, then there's a Zariski-dense set of preperiodic points, not just in the total space, but in every single fiber. Because it is itself preperiodic in every fiber. This is defining a polarizable in fact, polarized, because it's already in PN, morphism. It has its own Zariski-dense set of preperiodic points, its own measure of maximal entropy, et cetera. So that T to the n-1 is detecting the measure of maximal entropy for the restriction to the invariant subvariety. Okay, so the condition certainly holds when X is itself preperiodic, again, because you have the density of the preperiodic points in the whole family at every single fiber. Okay? And so the interesting case is when it's not a family, a persistently post-critically finite family. So this is the interesting case. And this is the case where that current is precisely the bifurcation current as defined, well, I guess in the preceding paper. Oh, no. Wrong authors. Okay, so, yeah, sorry, 2 Bs only. In a 2007 publication of Bassanelli and Berthelot, where they introduced the bifurcation current for holomorphic families of maps on PN. What is its definition? It's exactly that. It's exactly this. Let me just write it down. Let me erase this not helpful picture and put in the definition. So the bifurcation current, by definition, is you take this current, exactly the same thing, in the family. You take its top wedge power, by which I mean you're really thinking of, again, the family of measures over lambda, and you wedge it with the critical locus, the current of integration along the critical locus. Now, of course, usually we think of this as living on the parameter space, so we can push this down to lambda. But this is the definition of the bifurcation current. The one-dimensional case is what I had studied in my thesis, and this brought it to sort of general dimensional case. One can define this notion. One can just declare the family by definition. The family is stable if this current vanishes. So one can just define stability in this way. And then in dimension 1, I had shown that that was equivalent to sort of the usual notions of J stability that have been studied, that were introduced by Magnier, Sullivan, and Lyubich. And in higher dimensions, they started to study some of the properties here, and then it was in this paper by the 3 authors where they provide a collection of interesting characterizations dynamical characterizations of what stability means. I mean, this is just the vanishing of a current. It's not a priori obvious what it would tell you, but it turns out that stable has all sorts of nice dynamical implications. And I just want to mention, since I'm mentioning characterizations of stability, the brand new preprint, has it been posted? 2025, of Xavier, who's here in the room, together with Francois, which adds to this list of characterizations. So the vanishing of this current is equivalent to a holomorphic motion of repelling periodic points in the Julia set, which they had proved under just a few extra hypotheses. But they realized that actually it works in all families. So yeah, that the vanishing of this current locally, not even just not for algebraic families, it's a local statement over a complex manifold, that stability in this sense is equivalent to a holomorphic motion of the repelling periodic points in the Julia set in the support of the measure. Xavier, did I get that right? Is he listening? Is he here? So, well, one can define it in exactly the same way that we define it, as some injective map. You're following the points, and each individual one is being parametrized holomorphically, and it's a family of injections.
What is the improvement?
Pardon?
What is the improvement?
Yeah, so in this case, I believe that particular characterization, so there was a series of characterizations done in general, but it was, here it's over an arbitrary complex manifold. Here, if Christoph can correct me, but it was, that particular characterization was known when lambda was the full family, the entire family of maps, either of endomorphisms or maybe of polynomial maps. In dimension 2, I think it was for arbitrary lambda. Christoph, do you recall? In dimension 2, I think it was for arbitrary parameter spaces. But in higher dimensions, you needed the full family because I think the construction involved something with certain lattice maps or something that you're building. Anyways, there was some reason that they didn't yet know how to characterize in general.
Can I come back also to what you said? I didn't quite follow. So when X is preperiodic, then okay, it's a family of PCF, and when it's only phi special, it also implies it's a family of PCF.
Yes, so the thing is when they commute, yeah, so it's not, oh, this I don't know. Right, sorry. If it's only phi special, then a priori it's not itself preperiodic, so there could be an exception. There could be, but probably there's not. And that has not been proved. Yeah, sorry, that has not been proved, yeah.
But in higher dimension, in the absence of a general lambda lemma, does it really imply holomorphic motion of this small g?
It does not. In the absence of a lambda lemma, and things can go wild and complicated, right? So there is not a lambda lemma that guarantees the motion of the entire support of the measure. I think you could still, in principle, have collisions. I don't know myself offhand examples, but
I think there are examples when there is a Ziegel disk which collapses.
but then you won't have. Can you do that in a stable family?
As an example in the paper where this happens, that
In a stable family that you can have. Oh, really? Oh, okay. I don't know.
Okay, maybe I'm wrong.
I don't know. Maybe Romain, do you know? Okay. All right.
I'm surprised.
Yeah, it sounds fishy, but could be. So anyway, so this was all to say. In the very special case, oh, there's more to say. Sorry, there's one more thing to say. So what does the conjecture actually suggest to us? Does it tell us anything new about stability? If it were true, I don't even know if it's true, of course. But what does the conjecture suggest? It says, so this is something I was saying before, let me repeat it. So we have various characterizations of stability. In dimension 1, we know that if it's an algebraic family, so not just any old complex manifold, but an algebraic family of maps over a whole quasi-projective lambda, then stability in the whole family guarantees either isotrivial, meaning they're all the same map, or that you're back in this special situation. So again, in dimension 1, stability for the whole family guarantees that if it's non-trivial family, that that X is itself special, that you're back in this relative special dimension case. We don't know that if that's true in higher dimensions. But what this does tell us, what the conjecture would say, is if it's an algebraic family and if it's stable, then either it is PCF special itself, PCF special, it is special, or in the case where it might not be special, there are just very few periodic points or preperiodic points in the critical locus, that they are not Zariski-dense. That stability would mean that current vanishes, so the preperiodic points are not Zariski-dense. Okay, so it would be an additional characterization of stability in terms of preperiodic points that are not necessarily repelling, let me add. So here we know that in the absence of stability, so when it's unstable, one of the things proved in BBD implies so the density of what they call Mizurevich parameters, which are parameters where repelling periodic points are crossing your critical locus. Okay, so if it's an unstable family, then you get lots and lots of repelling periodic points. That's related to the 2 implies 1. That's a special case of the 2 implies 1. Instability implies lots of repelling periodic points. Okay? Lots of repelling periodic points, instability. But what I believe to be true is that lots of any preperiodic points would imply instability, unless they're persistent. But whether they're repelling or not, and we don't know how to prove something like that. So this conjecture is open even in the case of critical locus. Even in dimension 2. So it's only known in dimension 1. Yes, yes. Yeah, well, I could sort of formulate it as a conjecture, I suppose. But let me just repeat it here. So 1 implies 2 of the conjecture for x equaling the critical locus implies that stability of the family would be equivalent to, either x is the critical locus is special, meaning it's like persistently PCF or perhaps some other weird thing, or, and this is what I said, the preperiodic points are not. So I'm just rephrasing, but I want to, are not Zariski-dense in the critical locus. So in particular, and this is what I just said, in particular, a Zariski-dense set of preperiodic points non-persistently, whether repelling or not, and this is my key point, whether repelling or not implies instability. Not in the Julia set. Doesn't matter. That's the point. They could be attracting. But they can be repelling or not in the Julia set. Right. So whether repelling in J or not. Right. Yes. Yes. That's right. That if you just, which is a very strong statement and seems like it couldn't be true. So I don't know. It makes me question whether or not this conjecture is true or not. But I don't know, it's a statement. And I would love to know. If you disprove it, I would be happy with that too. I'd be okay with that. Okay? So that is a statement. Sorry that it's a mess. Zariski-dense set, the existence of a Zariski-dense set of preperiodic points in this family X. And not in every fiber, but just in the whole family. Whether they're repelling or not should imply instability. Okay. Let me go back to that middle board, maybe. Oh, no. No, I wanted to take this one down. I just wanted this one. Okay. So the conjecture suggests a number of other things. I want to give an example. I won't have time for a couple examples, but maybe one more example of the kind of statement that it implies. And now I want to do an example of a statement, which is for sure true, because it has been proved by 3 of the people in this room. Let me just say a word about invariant subvarieties. So the statement of the conjecture is about points, the existence of preperiodic points and how they exist in families of subvarieties. One can also ask about preperiodic things of higher dimension, whether or not a given X contains preperiodic curves, or if X itself is preperiodic for some number of parameters, but not persistently so. So the conjecture implies another conjecture that I'm going to state. So suppose that X is, let's say, a family of subvarieties as before. So let's say, but let me give them a name. So they're k-dimensional subvarieties. So k is my fiber dimension, my relative dimension. With k, so it's not, in this case, a family of points, and it's not the total space. And suppose for a moment that this is some kind of universal family, that actually lambda projects dominantly to the entire moduli space of maps on Pn. So this is not, anyways, whatever, let me write it down. Suppose that sort of the natural map so there's a map from the parameter space to the moduli space of all maps. Maybe, well, it has to be well defined, and it doesn't have to be surjective, but let me say it's dominant. So either surjective or dominant. So this is the map that sends my parameter lambda to the conjugacy class of the fiber map of phi lambda. Okay, so M is my notation for the moduli space of all maps, the moduli space of all maps on Pn, or the space of all maps with the equivalence relation being conjugacy by automorphisms on Pn. So just suppose that this is surjective, say, or dominant. So it's really a full family. Okay, so this phi is parameterizing all the maps on Pn. So just assume that for the moment. Then the conjecture above implies, the following statement, then the set of lambdas for which the fiber of X is preperiodic is small, is not Zariski-dense. Okay, sorry, this conjecture is not known. The special cases are known in lambda. I don't know what I said earlier, but let me rephrase what I was saying. This is a conjecture, which is a special case of the above conjecture. I claim this is a special case of the above conjecture. Okay, so let me read it. So I'm saying, suppose I have a family of subvarieties that are not points, so I'm not following a periodic point, and are not, for example, I'm not following a point, and I'm not looking at the total space. And the statement is that the set of all specializations, particular parameters for which that subvariety becomes preperiodic, that should be rare. Yeah.
My feeling is that you are stating as a conjecture something that is stated as a theorem of practicability.
Right. No, I said that so Fakhrudin proved that in this situation, where I take a family of subvarieties, that this set cannot be all of lambda. So Fakhrudin tells me this. That this set will not be all of lambda. So it's contained, thank you, in some, countable, so it's at worst generic. It's contained in some countable union of proper subvarieties of lambda. And the conjecture is that in general, not only can X not be preserved for all maps, it should in fact be rare that it's preserved for this particular X. Yes. Yeah.
The Fakhrudin theorem is that general map has no preperiodic variety, or very general map.
Very general.
Very general, okay.
Very general only is what he says. That's the conclusion.
Could you repeat the question and answer?
So what is the statement that you get from Fakhrudin's? Is this set is it general or is it very general? General meaning, does it actually contain a Zariski open, which is what the conjecture wants, that the complement would be containing a Zariski open, or is the complement only very general, generic, the complement of countable, right? That this, by construction, sort of the equations making this preperiodic, it gives you. So if you say, I want it to be fixed, that's some subvariety of lambda. I want it to be period 2, that's another subvariety of lambda. So for everybody to understand what I'm talking about here. I want it to be period 3, that's another subvariety. Or I want it to be preperiodic with some given combinatorics. There's this countable collection of conditions that one can define that define a whole bunch of different subvarieties of lambda. Fakhrudin tells us that none of them are all of lambda. So this is contained in some countable union of proper algebraic subvarieties of lambda. But that countable union could cross over the entire lambda in a complicated way. And so what we believe is true is that countable union for this particular family of X's is actually contained itself in some proper subvariety. I don't know how to describe such a thing. Even in this case, we don't know how to describe such a thing. So I want to mention that it is a theorem, a recent theorem, and a hard theorem of Gautier, Tofflin, and Vigny that shows that at least in the case of the family of hypersurfaces, which are the critical loci for these maps, that it is rare to be post-critically finite. Okay, so remember, for this to be PCF, so if the critical locus at a particular parameter, x lambda, being preperiodic, is the definition of being post-critically finite. So this is saying, so in other words, the set of all, well, I have a condition there, so of course it's important that n is bigger than 1, otherwise it's vacuous. The set of all PCF maps inside the moduli space is contained in some proper subvariety, a proper subvariety, in any degree and any dimension bigger than 1. In dimension 1, they are Zariski-dense, so that fails. That corresponds to, it's like the point case. This fails. Okay. So it's an example of a kind of conjecture which is a consequence of this other one. Why is it related, by the way? It's not obvious that it's related, I guess, the way I've written it. In fact, when I first spoke about this conjecture, I guess exactly 1 year ago at a conference in India, and Charles asked me the question, oh, does this conjecture contain this theorem as a special case? And I said, no, it couldn't possibly. I was sure it was not possible. I just hadn't really thought it through. And then I asked Myrto later, she was like, of course it does. So anyway, so I have to trust. And then I said, oh yeah, you're right. Okay, and then it actually turned out to be quite a bit of work to realize like that this statement is a consequence of the conjecture. And what is just to give you a hint of how they're related before I finish, the proof is, like the idea is sketched in the notes, but let me just say one thing to connect these two. The point is, that if you're at a particular parameter where that slice, that fiber becomes preperiodic, so if x lambda is actually preperiodic for your one map, this is a fact we've said before, then the restriction is its own polarized dynamical system. It has its own repelling periodic points that are Zariski-dense in the space. So preperiodic points are Zariski-dense in that fiber. So it's not just that you will get density of points in the whole family and maybe scattered in each fiber, but they're actually Zariski-dense in every fiber, which becomes preperiodic. Okay? And so, moreover, if they're Zariski-dense in x lambda, then if you start looking at products of x lambda with itself, and you look at the product map, f lambda crossed f lambda dot dot dot. Okay, so we have, this is going to seem a silly thing to do, but bear with me. If I know that they have the Zariski-dense set of points in this space, then it's also the case that they're Zariski-dense in the product space. You just take all the tuples, all the products of the periodic points. So this will be true. Let's say you take the m-fold product of the maps and of the things. This will be true. So also Zariski-dense for this new map, this product map, in x lambda to the m for all m. Okay, so that's the starting point to connect the conjecture to this, is that for every power, it's still Zariski-dense. Okay. So now, if I assume that this set is also Zariski-dense, the set of parameters is Zariski-dense. So if the set of parameters is also Zariski-dense in the parameter space, then if I take some kind of fiber power of my x, of my curly x, so I'm thinking of this now as in lambda cross Pn to the mth power, so then I can, at every fiber I take the power So I have Zariski density in every fiber of the product in a Zariski-dense, in the fiber for a Zariski-dense set of parameters. Then I also get Zariski density of periodic points in here. Okay? So there's also Zariski density in every power for the whole family. Okay, and where does the contradiction come, or why is this not possible if you assume the conjecture? This is every power. The point is that Fakhrudin's work, which is really a theorem about monodromy action on periodic points, what he actually proves, I haven't told you like how this goes, but what he actually proves is that if you follow periodic points over lambda, the monodromy action going loops around your lambda is transitive action. This is what he actually proves to prove this. And one can use that same type of argument to prove that the relative special dimension for the original x, and indeed for every single power, is always maximal. So do I have 1 minute? Oh no, I'm out of time. Oh no, we started 2 minutes late. One last thing. Oh, I shouldn't use this one because I'm going to cover up what I just wrote. So I'm almost done. Okay, it'll take me 2 minutes to rearrange the boards. Well, yeah, I guess I could have squeezed it in here and erased your theorem, but I didn't want to do that because this is what I'm discussing. But since I have I can just erase the picture there. Okay, so what I wanted to say is using Fakhrudin's theorem, one can deduce that the relative special dimension for x and for every fiber power of x is maximal. And then you contradict the positivity of this current because of a dimension count. It's just a dimension count. So let me just write this in words to complete why the conjecture should imply that this won't work. So via the theorem of Fakhrudin, it implies one can use it to show not only that the relative special dimension of x has to be n, but in fact that when you take these mth fiber powers and you take the product maps, that they're always maximal for all m, for all powers. And so condition 1, so the conjecture, so if you assume the Zariski density of those parameters, you have condition 1 holding in the conjecture for xm. The conjecture then, the hard implication of the conjecture, the questionable implication of the conjecture is that 1 implies 2, the one that may not even be true, but it implies that this current for the mth power, this is the maximal one, this is the measure of maximal entropy, mind you, is non-zero. But look, we're in trouble. This is an mnth power. The dimension of this thing is the dimension of lambda plus m times k, which was the fiber dimension of my x. This is strictly less than n. So as m gets large, so for m large, this is a contradiction. That current cannot be positive because you cannot have an mn current on a thing of dimension smaller than mn. It cannot support a current whose degree is too big. And so the upshot is that that set of parameters could not have been Zariski-dense. And I was going to state another conjecture, but I won't. So I'm done for now. You'll have more of me this afternoon.